Ammonium bisulfide corrosion or alkaline sour water as a part of uniform or localized loss in thickness phenomena. Description of ammonium bisulfide corrosion or alkaline sour water based on API 571, Number A, aggressive corrosion occurring in hydroprocessing reactor effluent streams and in units handling alkaline sour water. Number B, several major failures have occurred in hydroprocessing reactor effluent systems due to localized corrosion. Ammonium bisulfide corrosion, also known as alkaline sour water corrosion, is a specific form of chemical degradation that affects metals and alloys exposed to environments containing ammonium bisulfide, NH4HS, under alkaline and sour conditions. This type of corrosion is characterized by both general, uniform, and localized attack mechanisms, which can lead to significant material damage if not properly managed. Overview of ammonium bisulfide corrosion or alkaline sour water. Ammonium bisulfide is a sulfur-containing compound that forms in various industrial processes, including oil refining, petrochemical operations, and waste treatment. It is often encountered in sour water systems, where it contributes to the corrosive environment. Its presence, especially in alkaline conditions, creates a highly aggressive medium that interacts with structural metals such as carbon steel, stainless steels, and other alloys. Chemical environment and mechanisms of ammonium bisulfide corrosion or alkaline sour water. Chemical composition. The environment typically contains ammonium ions or NH4, bisulfide ions or HS-, and hydroxide ions or OH- due to alkalinity. Corrosive action. The bisulfide ion reacts with metal surfaces to form metal sulfides, which may be protective or non-protective depending on the conditions. The alkaline environment influences the stability and solubility of these sulfides. pH range. Corrosion is most significant in environments with a pH greater than 7, where alkaline conditions promote certain reactions that accelerate metal degradation. Types of ammonium bisulfide corrosion or alkaline sour water. General or uniform corrosion. In general corrosion, the material experiences a relatively uniform loss of metal thickness across the exposed surface. This occurs due to consistent chemical reactions between the metal and the corrosive species in the environment. The mechanism of general or uniform corrosion. The bisulfide ions diffuse uniformly across the metal surface, reacting with surface metal atoms to form metal sulfides and soluble ions. The continuous formation and removal of these layers result in a steady, uniform thinning of the metal. The effects of general or uniform corrosion. Over time, this uniform attack can compromise the structural integrity of equipment, leading to thinning and potential failure if not monitored and controlled. Factors influencing uniform corrosion includes temperature, concentration of ammonium bisulfide, pH and alkalinity levels, flow conditions, static or turbulent, material composition and surface finish. Number 2 of the types of ammonium bisulfide corrosion or alkaline sour water is localized corrosion. Localized corrosion refers to targeted attack on specific areas of the metal surface, which can be far more damaging than uniform corrosion. Common forms include pitting, crevice corrosion, and exfoliation. Pitting corrosion occurrence is small, deep cavities form where the protective film is disrupted, often initiated by chloride or other aggressive ions, but in ammonium bisulfide environments, pitting can develop due to differential sulfide ion concentrations. Crevice corrosion occurs in confined spaces such as joints, gaskets, or under deposits, where the local chemistry differs from the bulk solution, leading to acidification and intensified attack. The mechanism of localized corrosion. The localized breakdown of the passive or protective film occurs due to several factors, includes variations in chemical composition, differential oxygen availability, presence of aggressive ions like sulfides, microstructural heterogeneities in the metal. The effects of localized corrosion. Localized corrosion can lead to rapid penetration and failure of components, often without significant overall material loss initially, making detection more challenging. Factors promoting localized corrosion includes stagnant or low-flow areas, deposits or crevices restricting fluid flow, fluctuations in pH or sulfide concentration, use of susceptible materials. Corrosion products and the impact of ammonium bisulfide corrosion or alkaline sour water. The primary corrosion products in ammonium bisulfide environments are metal sulfides, for example ferrous sulfide, nickel monosulfide, chromium monosulfide, which may form protective or non-protective layers, protective films. Some sulfide layers can adhere tightly to the metal surface, reducing further corrosion. Non-protective or porous layers. Often, these layers are porous or loosely adherent, allowing continued access of corrosive species and promoting ongoing attack. Factors influencing corrosion severity of ammonium bisulfide corrosion or alkaline sour water includes temperature. Higher temperatures accelerate chemical reactions and increase corrosion rates. Chemical concentration. Elevated levels of ammonium bisulfide enhance the aggressiveness of the environment. Material compatibility. Different alloys exhibit varying resistance. Stainless steels with higher chromium content tend to be more resistant. Flow conditions. Turbulent flow can remove protective films, increasing uniform corrosion, while stagnant areas favor localized attack. Presence of other ions, chlorides, nitrates, or other ions can synergistically worsen corrosion. Mitigation strategies for ammonium bisulfide corrosion or alkaline sour water includes material selection, use corrosion-resistant alloys or coatings, environmental control, maintain optimal pH, temperature, and chemical concentrations, design considerations, minimize stagnant zones, crevices, and deposits, regular inspection. Detect early signs of localized corrosion through non-destructive testing. Ammonium bisulfide corrosion, in the context of alkaline sour water, presents a complex challenge involving both uniform and localized attack mechanisms. The chemical interactions between sulfide ions and metals can lead to the formation of various sulfide layers, which may either protect or accelerate corrosion depending on environmental conditions. Understanding these processes in detail is critical to developing effective prevention and mitigation strategies to ensure the longevity and safety of industrial equipment exposed to such aggressive environments. Ammonium bisulfide corrosion or alkaline sour water affected materials based on API 571, number A, carbon steel is less resistant, number B, 300 series SS, duplex SS, aluminum alloys and nickel base alloys are more resistant, depending on ammonium bisulfide, NH4HS, concentration and velocity. The materials affected by ammonium bisulfide corrosion or alkaline sour water are primarily metals and alloys used in industrial systems such as oil refineries, petrochemical plants, waste treatment facilities, and other environments where sour water containing ammonium bisulfide or NH4HS is present. The susceptibility of these materials to corrosion depends on their chemical composition, microstructure, and protective film formation capabilities. Common materials affected by ammonium bisulfide corrosion or alkaline sour water includes, number 1 is carbon steels. The vulnerability of carbon steel, highly susceptible to both general and localized corrosion in ammonium bisulfide environments. The mechanism of carbon steel forms iron sulfide layers when exposed to sulfide ions, which can be porous and non-protective under alkaline conditions, leading to accelerated corrosion. The implication of carbon steel usage in sour water environments is generally avoided unless proper corrosion allowances, protective coatings, or inhibitors are used. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 2 is low alloy steels. The vulnerability of low alloy steels, similar to carbon steels but with slightly improved resistance depending on alloying elements such as chromium, nickel, or molybdenum. The mechanism of low alloy steels, alloying elements can improve the formation of more adherent and protective sulfide layers. But in aggressive ammonium bisulfide environments, localized attack can still occur, especially in crevices or stagnant zones. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 3 is stainless steels. Type and resistance of stainless steels includes austenitic stainless steels such as 304, 316, moderate resistance, susceptible to localized corrosion such as pitting and crevice corrosion in the presence of sulfides under certain conditions. Higher chromium and molybdenum alloys such as 317, 904L, better resistance due to more stable passive films, duplex and superduplex. Stainless steels, offer significantly higher resistance to localized corrosion due to their dual-phase microstructure and improved corrosion resistance. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 3 is stainless steels. The vulnerability of stainless steels, sulfide ions can disrupt the passive oxide film, especially in crevices or stagnant zones, leading to pitting and crevice corrosion. The mechanism of stainless steels, material selection is critical. Higher-grade stainless steels are recommended for sour water environments. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 4 is nickel-based alloys such as Inconel, Monel. The vulnerability of nickel-based alloys, generally resistant to ammonium bisulfide corrosion owing to their stable oxide films and sulfide resistance. The mechanism of nickel-based alloys. Their high nickel content promotes the formation of protective nickel sulfide layers that inhibit further corrosion. The application of nickel-based alloys, widely used in highly corrosive sour water environments where high corrosion resistance is required. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 5 is titanium and tantalum alloys. The vulnerability of titanium and tantalum alloys, very resistant due to the formation of stable, adherent oxide layers. The application of titanium and tantalum alloys, used in extremely aggressive sour water conditions where other materials would fail. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 6 is nonmetallic materials, such as certain polymers, composites. Its vulnerability is typically resistant to chemical attack, however, their applicability is limited to non-structural components or lining materials. Common materials affected by ammonium bisulfide corrosion or alkaline sour water. Number 7 is coated and lined materials. The vulnerability of coated and lined materials, the base material's susceptibility depends on the coating or lining integrity. The implication of coated and lined materials. Proper selection and maintenance of coatings are crucial to prevent exposure of underlying metals to ammonium bisulfide. In-depth explanation, chemical interaction. Sulfide ions react with exposed metal surfaces, forming metal sulfides. These sulfide layers can be protective or detrimental, depending on their adherence and porosity. Localized attack. Materials with passive films, such as stainless steels, are vulnerable to crevice and pitting corrosion where the sulfide ions penetrate or disrupt the passive layer. Environmental factors, elevated temperatures, high sulfide concentrations, and stagnant or crevice-prone zones exacerbate material susceptibility. Material selection importance. Choosing materials with high corrosion resistance, such as nickel-based alloys or titanium, is essential in environments with high ammonium bisulfide content. In environments contaminated with ammonium bisulfide and alkaline sour water, the most affected materials are carbon steels and low-alloy steels due to their poor resistance to sulfide-induced corrosion. Stainless steels may suffer localized corrosion unless they are of high grade or properly protected. Nickel-based alloys, titanium, and tantalum provide high resistance but at increased cost. Proper material selection, protective coatings, and environmental control are crucial to mitigate corrosion damage in such aggressive conditions. Ammonium bisulfide corrosion or alkaline sour water. Critical factors based on API 571, number A, NH4HS concentration, H2S partial pressure, velocity, and/or localized turbulence, pH, temperature, alloy composition and flow distribution are all critical factors to consider. Number B. Corrosion increases with increasing NH4HS concentration and increasing velocity. Below 2 Wt%, solutions are not generally corrosive. Above 2 Wt% NH4HS, solutions are increasingly corrosive. Number C, in hydroprocessing reactors, FCC reactors and coker furnaces, nitrogen in the feed is converted to ammonia and reacts with H2S to form NH4HS. NH4HS precipitates out of the gas phase in the reactor effluent stream at temperatures below about 150 degrees Fahrenheit or 66 degrees Celsius, depending on the concentration of NH3 and H2S, and may cause fouling and plugging unless flushed away with wash water. Number D, NH4HS salt deposits lead to underdeposit corrosion and fouling. The salts are not corrosive unless they become hydrated, at which point they are very corrosive. Number E, oxygen and iron in the wash water injected into hydroprocessing reactor effluent can lead to increased corrosion and fouling. Number F, presence of cyanides increases severity of corrosion in FCC gas plants, coker gas plants and sour water stripper overheads by destroying the normally protective sulfide film. The critical factors influencing ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments, affecting both general, uniform, and localized corrosion, are complex and interdependent. Understanding these factors in detail is essential for predicting corrosion behavior, implementing mitigation strategies, and selecting appropriate materials. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water includes, number 1 is chemical composition of the environment, includes, the first is sulfide ion concentration. The level of ammonium bisulfide directly determines the availability of sulfide ions, which are highly aggressive toward susceptible metals. Higher sulfide concentrations increase the likelihood and severity of both uniform and localized corrosion by promoting more extensive sulfide metal reactions. The second is critical factors influencing by alkalinity or pH. The environment's pH influences sulfide stability and the formation of protective or non-protective sulfide layers. Elevated pH, alkaline conditions, pH greater than 7, can promote the solubility of certain metal sulfides, reducing passivity and increasing corrosion risk. Extreme alkalinity can also lead to microbially influenced corrosion or influence the nature of corrosion products. The third is critical factors influencing by presence of other ions. Chlorides, nitrates, and other halides can synergistically accelerate localized corrosion, especially pitting and crevice corrosion, by destabilizing passive films. Chlorides are particularly notorious for promoting pitting in stainless steels. The fourth is critical factors influencing by temperature. Elevated temperatures accelerate chemical reactions, diffusion rates, and sulfide formation. Higher temperatures greater than 50 degrees Celsius significantly increase corrosion rates and favor localized attack due to increased sulfide activity and destabilization of protective films. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water. Number 2 is material properties and microstructure, includes, the first is material composition. Susceptibility varies with alloy type. Carbon steels are highly vulnerable, while nickel alloys and titanium are more resistant. Chromium, molybdenum, and nickel contents influence the stability of passive films and sulfide resistance. The second is critical factors influencing by microstructure. Grain boundaries, inclusions, and phases can act as initiation sites for localized corrosion. Microstructural heterogeneities make certain areas more prone to crevice or pitting attack when exposed to sulfide ions. The second is critical factors influencing by surface finish. Rough or corroded surfaces with microdefects provide initiation sites for localized attack. Smooth, clean surfaces promote uniform corrosion but are not immune to localized attack if other factors are conducive. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water. Number 3 is environmental conditions, includes, the first is flow dynamics. Static or low flow zones promote crevice and pitting corrosion by allowing sulfide ions and other aggressive species to concentrate. Turbulent flow can remove protective sulfide films, leading to increased uniform corrosion. The second is critical factors influencing by stagnant zones and crevices. Areas shielded from flow, such as gaskets, joints, or deposits, foster localized chemistry changes. These zones tend to become more acidic or sulfide-rich, accelerating localized attack. The third is critical factors influencing by temperature gradients and localized heating. Hot spots in pipelines or equipment can cause localized increases in temperature, promoting localized corrosion. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water. Number 4 is presence and nature of corrosion products, includes, the first is sulfide layers. The type, stability, and adherence of metal sulfide films influence corrosion progression. Non-protective, porous sulfide layers allow continued attack. Protective layers can slow corrosion. The second is critical factors influencing by deposits and buildup. Deposits of sulfides or other materials can create crevices, leading to crevice corrosion. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water. Number 5 is operational and mechanical factors, includes, the first is water chemistry fluctuations, changes in sulfide content, pH or temperature over time can destabilize protective films, leading to sudden localized corrosion. The second is critical factors influencing by mechanical damage, scratches, dents, or erosion can disrupt passive films, exposing fresh metal to sulfide attack. The third is critical factors influencing by operational stresses. Stress corrosion cracking may occur under combined tensile stress and corrosive environment, especially in susceptible alloys. Critical factors influencing ammonium bisulfide corrosion or alkaline sour water. Number 6 is environmental microbiology. If present, certain microbes can influence sulfide levels or produce corrosive metabolites, further intensifying corrosion. The critical factors determining the extent and type of ammonium bisulfide corrosion in alkaline sour water environments are multifaceted and highly context-dependent. Control and monitoring of these factors, such as maintaining optimal chemical conditions, selecting resistant materials, ensuring proper flow, and preventing crevice formation, are vital for minimizing both general and localized corrosion risks. Ammonium bisulfide corrosion or alkaline sour water affected units or equipment based on API 571, Number A, hydroprocessing units. Number 1. NH4HS salts precipitate in the reactor effluent streams when temperatures drop to within the range of 120 degrees Fahrenheit to 150 degrees Fahrenheit or 49 degrees Celsius to 66 degrees Celsius. Number 2. Fouling and/or velocity-accelerated corrosion may be found at air cooler header boxes, inlet and outlet piping of air coolers, as well as exchanger tubes, effluent separators, and piping into and out of the reactor effluent separators. Sour water draw piping from reactor effluent separators. Flashing may cause severe erosion corrosion downstream of control valves. See Figure 5.7, 2-inch CS elbow and straight section in a sour water line off the cold HPS on an HDT unit. Vapor line from the high-pressure separators. Hydrocarbon lines from reactor effluent separators due to entrained sour water. Vapor line from the high-pressure separators. Hydrocarbon lines from reactor effluent separators due to entrained sour water. Stripper column overhead sour water. Ammonium bisulfide corrosion or alkaline sour water affected units or equipment based on API 571, Number A, hydroprocessing units. Number B, FCC units. NH4HS concentrations are usually less than 2 Wt% but high velocities and/or the presence of cyanides can remove protective iron sulfide scales. Number C, sour water strippers. SWS high concentrations of NH4HS in stripper overhead piping, condensers, accumulator and reflux piping, and possible presence of cyanides. Number D, amine units. High concentrations of NH4HS may be found in regenerator overheads and reflux piping depending on unit operation. Number E, delayed coker. High concentrations of NH4HS may be found in the gas concentration plant downstream of the fractionator tower. The units and equipment affected by ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments are typically those involved in the processing, transportation, and storage of sour water and related fluids in chemical, petrochemical, and oil refining industries. Due to the aggressive nature of ammonium bisulfide, especially in the presence of other corrosive species and under certain operational conditions, various components are susceptible to both general, uniform, and localized corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water includes, Number 1 is piping systems. The application of piping systems is to transport of sour water, process fluids, or other corrosive liquids. The susceptible components of piping systems includes, carbon steel piping, highly vulnerable to both uniform thinning and localized pitting or crevice corrosion, stainless steel piping, susceptible to localized attack, especially in stagnant zones or crevices, alloy piping, nickel-based alloys more resistant but still susceptible in extreme conditions. The critical areas of piping systems includes, weld zones, discontinuities and residual stresses can promote localized attack, valves, fittings, and bends, turbulence and crevices increase corrosion risk, dead legs and stagnant sections, promote localized corrosion due to stagnant, sulfide-rich microenvironments. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 2 is heat exchangers. The application of heat exchangers is to heating or cooling sour water streams. The susceptible components of heat exchangers includes shell and tube shells. Corrosion may occur on the shell side where flow is slower. Tubes, especially in carbon steel or stainless steel, prone to pitting and crevice corrosion at tube joints or welds. Baffles and tube sheets, areas with crevices and stagnant zones are vulnerable. The corrosion risks of heat exchangers includes localized pitting at tube supports or imperfections, general thinning of metal surfaces due to uniform corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 3 is storage tanks and reservoirs. The application of storage tanks and reservoirs is storage of sour water, waste liquids, or process streams. The susceptible materials of storage tanks and reservoirs includes carbon steel tanks, susceptible to both uniform and localized corrosion, especially at welds, flanges, and seams. Lined or coated tanks, protective linings can degrade over time, exposing the substrate. The critical areas of storage tanks and reservoirs includes bottom and sidewalls. High sulfide concentration zones may cause pitting, welded joints and penetrations. Common initiation sites for localized attack. Corrosion under insulation. Microenvironment under insulation can promote localized corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 4 is pumps and valves. The application of pumps and valves is to control and movement of sour water streams. The susceptible components of pumps and valves includes impellers, casings, and seals, susceptible to pitting and erosion corrosion. Valve seats and gaskets, crevice corrosion and leakage issues due to corrosion erosion. The risk factors of pumps and valves includes stagnant zones within valve bodies, cavitation or erosion combined with sulfide corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 5 is reactors and process vessels. The application of reactors and process vessels is chemical reactions involving sour water or other corrosive fluids. The susceptible areas of reactors and process vessels includes reactor internals, baffles, internals, and welds, vessel walls, especially in stagnant or low-flow zones, nozzles and openings, high risk of crevice and pitting corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 6 is scrubbers and gas treatment units. The application of scrubbers and gas treatment units is to removing sour gases or impurities. The susceptible components of scrubbers and gas treatment units includes absorber columns, internals and shells, spray nozzles, and packing. Corrosion can compromise performance and cause leaks. The corrosion mechanisms of scrubbers and gas treatment units includes localized attack at areas where flow is uneven or stagnant. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 7 is liners and coatings. The application of liners and coatings is protective linings inside tanks, pipes, or vessels. The vulnerabilities of liners and coatings includes coating degradation or failure exposes underlying metal to ammonium bisulfide. Crevices or holidays in coatings are common initiation sites for localized corrosion. Affected units and equipment by ammonium bisulfide corrosion or alkaline sour water. Number 8 is other auxiliary equipment, sample lines, drains, and instrumentation. These often have crevices or stagnant zones prone to localized attack, gaskets and flanges, susceptible to crevice corrosion if not properly maintained or protected. The impact of ammonium bisulfide corrosion in alkaline sour water environments is far-reaching across many types of equipment and units within process plants. The most vulnerable areas are typically those with stagnant zones, crevices, welds, or coatings that have degraded. Understanding these susceptible units allows for targeted corrosion management strategies, including material selection, design improvements, corrosion inhibitors, and regular inspection. Ammonium bisulfide corrosion or alkaline sour water. Appearance or morphology of damage based on API 571, Number A, general loss in thickness of carbon steel, with the potential for extremely high localized rates of wall loss can occur at changes in direction or turbulent flow areas above 2 Wt% concentration. Number B, Low velocities may result in extremely localized underdeposit corrosion if insufficient water is available to dissolve the NH4HS salts that precipitated. Number C. Heat. Exchangers may show plugging and loss of duty due to fouling. Number D. NH4HS rapidly corrodes Admiralty brass tubes and other copper alloys. The appearance and morphology of ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments, whether it manifests as general, uniform, or localized corrosion, are characterized by distinctive features that reflect the underlying corrosion mechanisms, environmental conditions, and material susceptibility. Appearance and morphology of ammonium bisulfide corrosion or alkaline sour water includes, number 1 is general or uniform corrosion morphology. The surface appearance of general or uniform corrosion includes thinning and roughening. The surface becomes uniformly thinner and rougher over time due to consistent metal loss. Matte or dull finish. The smooth metallic shine diminishes, resulting in a matte appearance. Color changes. Often, a darkened or tarnished surface develops due to the formation of metal sulfide films or corrosion products. Corrosion products of general or uniform corrosion includes metal sulfides. Uniform layers of metal sulfides such as ferrous sulfide, nickel monosulfide, may form, which can be adherent or loosely attached, porous or cracked films. These layers tend to be porous, non-protective, and may crack due to internal stresses, exposing fresh metal to further attack. Surface features of general or uniform corrosion includes no distinct localized features. The corrosion tends to be evenly distributed without specific pits or localized attack zones. Micro-roughness, increased micro-roughness at the microscopic level, observable under SEM, scanning electron microscopy. Appearance and morphology of ammonium bisulfide corrosion or alkaline sour water. Number 2 is localized corrosion morphology. Description. Localized corrosion such as pitting, crevice corrosion, or microgalvanic attack exhibits more distinctive and aggressive morphological features, includes. Number of the localized corrosion morphology is pitting and pockmarking. The appearance of pitting and pockmarking includes small, deep, rounded or irregularly shaped pits on the surface. Pits vary in size, typically ranging from micrometers to millimeters in diameter. The surface around pits may remain relatively smooth or show signs of slight thinning. The features of pitting and pockmarking includes, pits often have sharp or sloped walls, due to rapid metal removal at the initiation site. Pits may be filled with corrosion products. Dark sulfide deposits or oxide layers may lodge within pits. Pitting attack can lead to fracture initiation. Critical and structural applications. Number B of the localized corrosion morphology is crevice corrosion. The appearance of crevice corrosion includes localized attack within crevices, such as gasket areas, weld seams, or under deposits. The affected zone appears as darkened, corroded regions with uneven or rough surfaces. The features of crevice corrosion includes corrosion products, thick, adherent sulfide-rich deposits or corrosion scales, undercutting of the surface. The corrosion often proceeds beneath deposits or within crevices, leading to cavity formation. Number C of the localized corrosion morphology is erosion corrosion. If flow-induced, the appearance of erosion corrosion includes surface shows signs of roughness and gouging, often in areas with high fluid velocity, leading to mechanical removal of corrosion products and metal. Appearance and morphology of ammonium bisulfide corrosion or alkaline sour water. Number 3 is corrosion products morphology, includes metal sulfide layers, usually dark, flaky, or powdery deposits, can be adherent or loosely attached, depending on the environmental conditions and alloy composition, porous or cracked films, non-protective, often facilitating further localized attack. Another corrosion products morphology is from oxide sulfide mixtures. Some environments may produce mixed oxide and sulfide scales, leading to heterogeneous, layered structures. Appearance and morphology of ammonium bisulfide corrosion or alkaline sour water. Number 4 is microscopic and SEM features, includes, the first is pitting morphology, deep, narrow pits, often with corrosion fronts extending into the metal, ferrous sulfide or nickel monosulfide deposits, visible at the bottom of pits, corrosion fronts, sharp interfaces between affected and unaffected metal. The second of microscopic and SEM features is crevice areas, includes localized corrosion with undercutting or cavity formation, deposits of sulfides and corrosion products within crevices. The third of microscopic and SEM features is surface roughness, increased at both the macro and micro scales, presence of microcracks within sulfide layers or corrosion scales. Appearance and morphology of ammonium bisulfide corrosion or alkaline sour water. Number 5 is visual indicators of ammonium bisulfide corrosion, includes, the first is coloration, dark brown to black patches due to metal sulfide deposits. Some sulfides may appear as bluish or greenish tarnishes depending on the metal. The second is surface texture, from smooth and mild uniform corrosion to rough, pitted, or uneven and localized corrosion, and the third is deposits, presence of flaky, powdery, or crusty sulfide deposits, especially at pits or crevices. The morphology of ammonium bisulfide corrosion reflects its aggressive chemical nature, particularly under conditions favoring sulfide formation and stability. Recognizing these features helps in diagnosing corrosion severity, understanding failure modes, and implementing suitable mitigation measures. Ammonium bisulfide corrosion or alkaline sour water prevention and mitigation based on API 571. Number A, good design practice should consist of symmetrical and hydraulically balanced flow in and out of air-cooled exchangers. Number B, carefully review design and localized velocities as process conditions change, particularly as NH4HS concentrations exceed 2 Wt% and begin to approach 8 Wt% or higher. Number C, maintain velocities within industry guidelines of 10 to 20 frames per second for carbon steel. Carbon steel may be susceptible to high corrosion rates above about 8 Wt% NH4HS concentration. Number D, use resistant materials of construction, such as alloy 825, duplex SS, at velocities above 20 frames per second, depending on NH4HS concentration. Number E, properly design and maintain water wash injection with low oxygen content, provide sufficient excess water to ensure that an adequate amount of water remains as liquid to dilute the NH4HS salts. Use proper injection spray nozzles and metallurgy. Number F, titanium and alloy C276 have been used in overhead condensers in SWS units. Number G, aluminum exchanger tubes are extremely susceptible to erosion-corrosion damage. Preventing and mitigating ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments requires a comprehensive approach that addresses both the chemical nature of the corrosive species and the operational conditions that promote corrosion. Below is a detailed overview of effective strategies, tailored for both general, uniform, and localized corrosion. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water includes, number 1 is material selection, includes, number A, use corrosion-resistant alloys, high-performance materials, includes, nickel-based alloys such as Inconel, Monel, duplex stainless steels, or other corrosion-resistant alloys offer superior resistance to sulfide-induced attack. Advantages: reduced corrosion rates, especially in localized attack zones, the limitations of using corrosion-resistant alloys, higher cost, may be limited in availability or fabrication. Material selection. Number B, coatings and linings. Protective coatings and linings can be used are included, epoxy, ceramic or rubber linings can act as barriers. Please be noted that coatings must be compatible with sour water environments and inspected regularly. For another, we can use cathodic protection by using sacrificial anodes or impressed current systems in storage tanks and piping. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water. Number 2 is operational control, includes, number A, control of pH and temperature, includes, maintain slightly higher pH, slightly increasing pH such as above 9 reduces sulfide species solubility and reactivity, control and manage the temperature, lower operating temperatures decrease sulfide corrosion rates. Use of heat exchangers or insulation to prevent hot spots. Operational control. Number B is flow management, includes, ensure turbulent flow, promotes uniform corrosion and prevents stagnant zones, avoid dead legs and stagnant zones, design pipeline and equipment to minimize areas where flow is sluggish, reducing localized attack. Operational control number C is control of sour conditions, includes, limit sulfide concentration, use chemical scavengers or remove hydrogen sulfide, H2S, and ammonium bisulfide precursors, maintain proper water chemistry, use buffering agents to stabilize pH, and adjust chemical composition to prevent sulfide accumulation. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water. Number 3 is chemical treatment, includes, number A, corrosion inhibitors, sulfite selective inhibitors, organic or inorganic inhibitors formulated to adsorb onto metal surfaces, blocking active sites, the application of corrosion inhibitors, continuous injection into process streams, with dosage optimized based on testing. Chemical treatment. Number B is neutralizing agents by using pH adjusters, ammonia or amines to maintain alkalinity, and avoid acidic conditions that exacerbate sulfide corrosion. Chemical treatment. Number C is scavengers and neutralizers, includes, sulfide scavengers, chemicals like ferric salts or zinc compounds trap sulfides, reducing free sulfide concentration. The limitations of scavengers and neutralizers is require regular dosing and monitoring. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water. Number 4 is design and engineering controls, includes, number A, equipment design, smooth, clean surfaces, minimize weld discontinuities, roughness, and crevices, use of proper seals and gaskets, prevent ingress of corrosive species into crevices, design for drainage and cleaning, avoid stagnant zones where ammonium bisulfide can accumulate. Design and engineering controls. Number B is inspection and maintenance, regular inspection, use non-destructive testing or NDT methods such as ultrasonic testing, radiography, or visual inspection, corrosion monitoring, install corrosion coupons or probes to track corrosion rates, timely repairs, replace or repair corroded sections before failure. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water. Number 5 is operational best practices, includes, maintain consistent water chemistry, regularly monitor pH, sulfide levels, and temperature, minimize exposure time, reduce the duration equipment is exposed to high sulfide concentrations, use of inert or protective atmosphere, for critical components. Inert gas blanketing can reduce oxygen and sulfide ingress. Prevention and mitigation of ammonium bisulfide corrosion or alkaline sour water. Number 6 is advanced and emerging technologies, includes, number A, surface treatments. Passivation, apply passivating layers that form stable, protective oxide films resistant to sulfide attack. Number B, molecular or nanotechnology coatings. Innovative coatings, development of nanocomposite or self-healing coatings for enhanced resistance. Number C, corrosion inhibitor formulations. Customized inhibitors, tailored formulations for specific process conditions. Effective prevention and mitigation of ammonium bisulfide corrosion demand an integrated approach combining proper material choice, process control, chemical treatment, and regular inspection. Tailoring these strategies to specific process conditions and equipment geometry enhances their effectiveness, ensuring operational safety and longevity of assets exposed to alkaline sour water environments. Ammonium bisulfide corrosion or alkaline sour water inspection and monitoring based on API 571. Number A carefully designed plan should include input from process engineers and materials/corrosion engineers to determine specific areas of vulnerability. Determine ammonium bisulfide content through sampling and calculation. Number B, frequent UT scanning and/or RT profile thickness of high and low velocity areas. Number C, UT downstream of control valves at high NH4HS concentrations. Number D, IRIS, RFEC and flux leakage inspection of steel air cooler tubes. Number E, EC inspect non-magnetic air cooler tubes. Number F, monitor water injection facilities and flow meters to ensure proper operation. Inspection and monitoring are critical for early detection, assessment, and management of ammonium bisulfide, NH4HS, corrosion in alkaline sour water environments. Different methods are employed depending on whether the corrosion is general, uniform, or localized, pitting, crevice. Below is a detailed explanation of the most effective inspection and monitoring techniques. Inspection and monitoring methods for detecting ammonium bisulfide corrosion or alkaline sour water. Number 1 is visual inspection. This is purposed to detect obvious signs of corrosion such as discoloration, pitting, cracking, or deposit buildup. The method of visual inspection are including, use borescopes, fiber optic cameras, or magnifying glasses for internal and inaccessible areas, examine surface roughness, blistering, or flaking. The indicators of ammonium bisulfide corrosion includes darkened or tarnished surfaces due to sulfide deposits, pits or cavities indicating localized attack, deposits of sulfide scales or crusts. The limitation of visual inspection is, it cannot detect subsurface or microscale corrosion, and it requires clean, accessible surfaces for accurate assessment. Inspection and monitoring methods. Number 2 is visual and microscopic examination of removed samples, includes, the first is using corrosion coupons. Metal samples exposed in the process environment are periodically removed. Measure weight loss, surface morphology, and deposit accumulation. The second is using microscopy, use optical microscopy or SEM, scanning electron microscopy, for detailed surface analysis. Identify micropitting, sulfide layers, and corrosion front progression. Inspection and monitoring methods. Number 3 is non-destructive testing or NDT techniques. NDT. Number A, ultrasonic testing or UT. It is purposed to measure wall thickness and detect internal or subsurface corrosion. The ultrasonic testing method is using ultrasonic transducers to send high-frequency sound waves into the material. It is working to identify areas of thinning or internal cracks. The ultrasonic testing or UT apply for suitable for pipes, vessels, and tanks, perform regular thickness surveys to track corrosion rates. NDT. Number B, radiographic testing or RT. It is purposed to visualize internal defects, cracks, or voids. The radiographic testing method uses X-rays or gamma rays to produce images of internal structure. The limitations of radiographic testing, less effective for surface corrosion, more suited for internal flaws. NDT. Number C, magnetic particle and dye penetrant testing. It is purposed to detect surface breaking cracks or defects. Its application is limited to ferromagnetic metals or surfaces accessible for surface preparation. Inspection and monitoring methods. Number 4 is corrosion coupons and probes, includes, number A, corrosion coupons. This is a metal strips or samples made of the same material as the process equipment. The placement of corrosion coupons, it is installed in process streams or tanks, monitoring using corrosion coupons, periodically retrieved for weight loss analysis, surface examination under microscopes. Helps quantify corrosion rate over time. Number B is electrochemical probes, includes, the types of electrochemical probes, linear polarization resistance, LPR, probes, measure corrosion rate based on electrochemical response, reference electrodes, monitor potentials indicative of active corrosion, advantages of electrochemical probes, continuous, real-time corrosion rate data. Inspection and monitoring methods. Number 5 is electrochemical monitoring, includes, number A, potential measurements, open circuit potential or OCP, monitor the electrochemical potential of metal surfaces, deviations can indicate active corrosion or passivation. Number B, electrochemical impedance spectroscopy or EIS. It is purposed to assess corrosion resistance and the integrity of protective films. This method apply a small AC voltage and measure impedance to evaluate surface condition. Inspection and monitoring methods. Number 6 is chemical analysis of corrosion products, sample analysis, extract corrosion deposits or scale for chemical identification, use techniques such as XRD, SEMEDS, or FTIM. The purpose of chemical analysis of corrosion products is to confirm sulfide-rich corrosion products, assess sulfide concentration, and understand corrosion mechanisms. Inspection and monitoring methods. Number 7 is advanced techniques, includes, number A, fiber optic sensors. Its application is to continuous monitoring of corrosive parameters like pH, sulfide concentration, or temperature at critical sites. Number B, acoustic emission monitoring. It is purposed to detect active crack growth or localized failure events in real time. Number C, digital imaging and AI-based analysis. It uses high-resolution cameras and image analysis software to monitor surface changes over time. Inspection and monitoring methods. Number 8 is inspection frequency and strategy, includes routine inspections, visual inspections complemented by thickness measurements every 6 to 12 months, condition-based monitoring, continuous electrochemical measurements or sensor data to identify early signs of corrosion, periodic sampling, regular extraction and analysis of corrosion deposits and water chemistry. Accurate detection and monitoring of ammonium bisulfide corrosion are essential for safe operation and asset longevity. Combining multiple techniques, visual, electrochemical, ultrasonic, and chemical analysis, provides a comprehensive understanding of the corrosion state, allowing for timely maintenance, process adjustments, and mitigation strategies. Thank you.